Our next speaker is Dr. Sam Ivey from the University of Mary Hardin-Baylor, who is hosting this event, and he will talk to us about classifying the finite structures of involutions acting on root systems. It's all yours, Sam.
Great. Thank you, Dr. Snow. I appreciate the intro. Hello, everyone. I'm excited about being here today and talking about this particular research interest of mine that have trailed me throughout my tenure here. So tenure at UMHB and in previous years. This is an introductory talk as best I can into some of the things that interest me. So the outline for today, just a little bit of motivation of my problem, some background, what I mean by fine structures, and then I'll wrap it up and address any questions that you may have. So I'm a lead theorist by training, LIE. A lot of people read that and think lie and think I'm a lie theorist, and so they don't trust me at first when I say this. But Lie theory is my area of interest, and Sophus Lie, the Norwegian mathematician, is credited to be the father. He sort of stumbled upon this Lie theory with his exploration within analysis and differential equations and looking at symmetries within that. And well, after this discovery, people began to say, hey, these things have nice structure, plays well. Let's lump everything under Lie theory. So that includes Lie groups, Lie algebras, and root systems, which is what I'm focusing on today. So after this explosion of Lie theory in the late 1800s, some of the topics that sort of squeezed out was this notion of symmetric spaces. And I have this G modulo H here. Now, there are various representations of symmetric spaces depending on one's discipline, context, research area. But for me, what we're looking at is this group, this Lie group or algebraic group modulo this H, which is a fixed group. And within these symmetric spaces, what I'm interested in is characterizing what we're calling these real symmetric varieties. I'm not going to get into that definition because that goes off into outer space, and I'm trying to stay as closely tethered to this terrain as possible. But this is where I'm sort of drawing my attention to characterizing these symmetric spaces. And because I am in this very abstract area of algebraic groups or Lie groups, whatever they may be, it was sort of difficult to sort of figure out how can I begin to address some of the questions that fall into this characterization of these varieties. And it was for the help of brilliant mathematicians who have come well before me, Cartan, Killing, Chevalier, Sear, who sort of connected all of these pieces, the Lie group being associated to a Lie algebra and the Lie algebra being associated to root systems, and that correspondence going in both ways. So they are all connected. So the challenging questions that are posed with characterizing symmetric K varieties or symmetric real varieties can be realized in some way by looking at a simpler representation in that of root systems. So what are root systems? If we start with a subset of a finite Euclidean space, so the reals, for example, or reals with some dimension greater than 1, we have a root system if these following axioms hold. So phi is finite, it spans E, it does not contain the zero vector. And if we take an element, we call it a root. If we take a root of our root system, the only thing that's in there is the root itself and the negation of that root. And for every root, there's an associated reflection, this sigma sub alpha, that leaves phi invariant, which means it maps phi to itself. And it doesn't map to an element outside of my root system. And then this last condition, in general, will be this inner product between these two vectors, beta and alpha. But in our case, and in the context of this talk, think of it as the dot product for those students who have had some calculus 3, or was just fortunate to have a great conversation with one of their professors one day, and they just stumbled upon the conversation of dot products. I would like to have that conversation with some of my students, but it hasn't happened yet. But, well, outside of calculus 3. But we have these reflections, and we define these reflections as, so sorry, I got a little excited there. But essentially what these reflections are, as the name suggests, is the ability to reflect across a hyperplane that's associated with each of these alphas. So once again, I mentioned that our Euclidean space will be the n-dimensional real space. So we take the standard orthonormal basis elements of Rn, that is E1 having 1 in the first entry, 0 elsewhere. E2, 1 in the second entry, 0 elsewhere. So EI would be 1 in the ith position, 0 elsewhere. And of course, En, the last basis element, will be 1 in the nth position. And we use these base elements to construct our roots for all the types of root systems that I'll talk about today, but only highlight a few. So let's start with an example. The professor and me, I give a definition. I like to give an example. So let's take R2, for example, and let's describe phi to be the set only containing these two elements, E1 minus E2, E2 minus E1. If you want the vector notation, there you go. It is the ordered pair 1, -1, which is the vector in purple, and then the ordered pair -1, 1, which is the vector in yellow. Can you see? I'm showing my crude pride here. So it only consists of these two vector elements here. So let's check the axioms to make sure that this phi, which is a subset of a Euclidean space, is actually a root system. So phi is definitely finite. I count 2 elements. You count 2 elements. It spans this vector 1, -1, because that's exactly what E1 minus E2 is. It does not contain the 0 vector. I don't see it in the set. It only contains 2 elements. My first root, E1 minus E2, and the negation of E1 minus E2. And all reflections send E1 to E2, E1 minus E2 to E2 minus E1, and vice versa. So if you were to zoom into the graph on your right, their reflection will be where they intersect, where they meet at the origin. So if I were to draw so think of the hyperplane being actually the line y equals x. So if I were to reflect the purple arrow across the y equals x line, I get the yellow, and vice versa. If I were to reflect the yellow line across the line y equals x, I get the purple. So that's what my reflection is doing. And to give an example of the fourth condition with the dot product that I mentioned earlier, if I were to take these 2 elements and push them through that ratio, so I have 2 times my alpha comma beta, and then beta beta, so my alpha is the E1 minus E2, my beta is the E2 minus E1, and I perform this inner product, this dot product between these two. It actually simplifies into an integer, -2. So, hooray, this phi is a root system. And this phi is a particular type of root system. It is a root system of type A1. So I want to give you more examples of root systems, more pictures, more graphs of several roots. So you see in the first left-hand corner, A1 cross A1, which sort of favors R2 for us. So we can sort of see there may be some isomorphism there. You have A2 you have B2, and then the one that that does not have an initial is actually D2. But you have G2 and, sorry, my screen is, minimize this. All right. And then C2. All right. So these are rank 2 polynomials, meaning that they have a dimension of 2. That's what we sort of associate dimension for vector spaces, rank for root systems. And you can sort of see some isomorphy happening a little bit here in the first column. If I were to rotate the first picture a few degrees, I want to say 45, I believe. If I were to rotate that 45 degrees, I actually get the picture below it. And likewise for the last column, B and C, there is some isomorphy action going on there. And that is generally the case between root systems of type Bn and of type Cn as well. So there is a lot of geometry that is occurring here behind the scenes. Now, once we move beyond these rank 2, it becomes very challenging to try to picture what those graphs of these roots and root systems will look like. So we often switch from one pictorial representation to these Deacon diagrams, where each of those nodes represent roots of my root system. And in particular, they represent a basis. So if we have a root system, which is the subset of this Euclidean space can be generated by bases, then let's use bases for our root system. So these nodes represent our simple roots. That's what we call our base elements. And it represents the relationship between each of the roots. So if they are connected by an edge, that means that the dot product essentially is equal to -1. If they're not connected by an edge, that means the dot product is equal to 0. And then what you see in B and Bn and Cn is that those arrows show a relationship, but it also shows pointing to a shorter element or a longer element, or a shorter simple root or a longer simple root. So we have the classical, what are considered the classical root systems, An, Bn, Cn, and Dn. And then you have the exceptional root systems, not to say that they perform better than the classical, but exceptional in a different context, E6, E7, E8, F4, and G2. So, sorry, I don't want to be moving too quickly here. So I'll go back a little bit, maybe one culture eye a little bit. So for this talk, I won't show all of these involutions, acting on all of these root systems. That's what I did previously. But I want to highlight a few because some do something special with particular involutions, and I'll describe what I mean by all of that. So let's get to this notion of involutions, and let's consider wild groups. So remember those reflections that I mentioned when I was talking about root systems? Well, let's gather all of those reflections. If we collect all of those reflections, they create a group called the wild group, which is associated with or a subset of the automorphism groups of phi. So these are all the very nice mappings, operation preserving, distance preserving mappings. These are symmetries for our Euclidean space. Now we can represent, or we could talk about all the wild groups of all of those root systems that I discussed earlier. But once again, I'm trying to focus on these three: An, Dn, and E6 being the type of root systems. For the wild group of An, we have the permutation group, Sn plus 1. This Dn is represented by this is called the semi-direct product. If this is foreign to you, don't worry about it. What it essentially means is very connected to the permutation group, in that there are Dn, the wild group of Dn is a subgroup of the signed permutation groups. And I'll give an example of a permutation in the next few slides. And then E6 is a bit more challenging to represent. But we know that the Weil group is essentially this group of automorphisms that has this very large order. So there are 51,840 such reflections in this particular group. So you can imagine the amount of fun in looking at all of those involutions. So let's look at an example. Let's look at the first example that I gave you with that phi being E1 minus E2 and then E2 minus E1. I mentioned that that was a root system of type A1. So the Weil group of that root system is actually S2, and that consists of two permutations, this iota. And think of the first row in this matrix as my domain and the second row as my range. So what that means, reading column-wise, 1 is mapped to 1, 2 is mapped to 2 for iota, and for sigma, 1 is mapped to 2, 2 is mapped to 1. For those who have seen permutation groups before, this is the 2-line notation for a permutation, but for those who have not, I hope that this makes some sense. So 1 goes to 1, 2 goes to 2 is the identity or iota, and then sigma, 1 goes to 2, 2 goes to 1. That's how we're reading those matrices there. All right, so let's look at how the permutation, how the elements in my Weil group act on those orthonormal basis elements. So if we define sigma to be, define sigma acting on this base element to be where it sends the index, where it sends the index of my orthonormal basis. So we can see, for example, sigma, this sigma that is defined in the example, sigma of E1, that is 1 in the first position, 0 elsewhere, is essentially E of sigma 1. Where does sigma send 1? And according to that, sigma sends 1 to 2. So sigma of E1 is essentially E2. So it sends one base element to another base element. So let's get to this notion of an involution. So if I take an element in my automorphism group, my Weil group, and this element is not the identity. I don't want the identity. That's a trivial case. So I want to ignore that. Theta is called an involution if theta squared of alpha is equal to alpha for every root in my root system. And by theta squared, I mean the composition of functions that you guys worked with back in college algebra and back in your early calculus 1 day. So we're just composing the function with itself. So once again, let's go back to that previous example. So we only have two options. Well, essentially we only have one because iota is the identity. It sends 1 to 1, 2 to 2. So it fixes everything. So let's look at this sigma and convince ourselves if this sigma is indeed an involution. And it actually is. So sigma of E1, we learned is just E2. So if I apply sigma again, the sigma squared of E1, the sigma of E1, we get E1 back. I thought I had the second one as well. But when you do the same thing for E2, then you will see that it also fixes E2. So what I am not seeing, again, could be a good exercise for those of you who are taking notes, is that I did not show the E1 minus E2, but we can do that as well. So sigma sends E1 minus E2 to E2 minus E1. But then it sends E2 minus E1 back to E1 minus E2, if all of that makes some sense. All right, so here's what we're doing. All the roots that are fixed by my involution, we're going to color black in those Deacon diagrams, those nodes, we're going to color those black. And those that are white, I mean, left not colored, are white, have this representation here in this second bullet. And these are called, these are elements of my restricted root system, which has a very large implication for the larger group. So in the example of root system of type A5, we have the Deacon diagram of A5. There is an involution that gives me something like this, where those three nodes are colored black, and that is of type A, that is of type 3A1, because those are three independent nodes. They have no connection to each other. And there's another involution that gives me this type. So with A5, there's a smaller root system of A3. And so what I discovered was that in red, we have these fine structures for these types of involutions. And so we have those independent nodes. We will have R of those independent nodes, and then we have some other parabolic subset that looks like either AL, BL, CL, DL. Those root system diagrams that I showed you guys earlier. And so I'll skip that for the time being. So it talks about the correspondence between the theta and my theta's Deacon diagram, but I'm running out of time. It's always such good stuff in a small amount of time. But anywho, so the relationship between the two is that if we're able to look at those the diagrams associated with my involution, there's a corresponding diagram automorphism for my opposing involution. Now, what this does is gives me the information needed to answer the question that I started off with in characterizing these K varieties. Now we can translate this information up to the larger space and sort of beginning to chip away at how we can begin the characterization of those very general parabolic subsets. So I wanted to give you guys the types for the type AN, DN, and E6. Those are just some of the examples. There are over 151 cases up to isomorphy, and I only have 20 minutes, so I couldn't go over those. Here are some of the references. Are there any questions?
Let's thank Dr. Ivy before we ask any questions.